Hi, I'm Corentin and today I'm reviewing another paper for marktechpost.com. So this is a paper which has made quite a bit of noise recently in the AI community, and the title is The AI Economist: Improving Equality and Productivity with AI-Driven Tax Policies. So the authors explain that one major problem in economics is finding the good balance between productivity and equality. Because of course, in an economic system, everyone tries to get richer. But if resources are limited, not everyone can become rich. And so this drive for productivity tends to create inequalities. To improve equality, we can apply a tax policy which takes more money from the richest people. The problem with such a tax policy is that it tends to discourage people from earning more money, which in turn reduces the overall productivity. And conversely, there exist systems where the richest pay a smaller tax fraction, which encourages productivity but isn't quite egalitarian. The goal of this paper is to find a tax system which would provide us with the best of both worlds. That study describes itself as a two-level reinforcement learning approach to learn dynamic tax policies. Reinforcement learning is typically used in the domain of video games, where the AI player is given a set of actions and tries to maximize a score. Here, for this game, we have two types of players: the agents, which represent individual actors of the market, and the government. The agents try to maximize their individual wealth, while the government tries to maximize the balance between productivity and equality. The simulation takes place on a map where two types of resources can be found: stone and wood. The first reinforcement loop is that of the agents. They start each iteration by observing their surroundings. Besides moving, they can perform several types of actions. They can either collect resources, build a house for which they receive money, or trade resources for money. The cycle is then completed by a phase of reinforcement learning where the agents assess and improve their respective strategies. The second reinforcement loop is that of the government, which observes the situation, applies a tax policy, and assesses the balance between productivity and equality. As said earlier, we therefore have a two-level learning system. Now, let's dive into the structure of the neural network. On the agent's side, we first have a convolutional neural network dedicated to observing the world. Indeed, this type of network is typically used in the field of computer vision. A multi-layer perceptron, which is a more generic type of neural network, is then used to combine this observational data with the knowledge that the agent has about the tax system and about its own internal state. On the right-hand side of the diagram, you can notice a private state. What is it? Well, each agent has a skill level which is unknown to the other agents and to the government. The skill determines the quality, and thus the value, of what is produced by the agent. In this case, houses. A highly skilled worker will therefore obtain more money when constructing a house. Finally, the data is processed by a long short-term memory recurrent neural network, which introduces temporality in the training that is performed over a long sequence of iterations. On the government side, the architecture of the neural network is nearly identical. Here, the output of the training isn't an action performed in the map, but a fine-tuning of various tax range brackets. In some simulations, this second learning scheme will be replaced by fixed tax policies that correspond to realistic scenarios. The efficacy of such scenarios will be compared with that of the full algorithm, featuring tax policy reinforcement learning. Multiple copies of each simulation are run, and the evolution of the tax policy score is computed. And it turns out that in these simulations, the AI government outperforms the other economic systems. To achieve this result, the AI government opted for a tax model that features two separate valleys of attraction. These valleys correspond to ranges of income that will represent the tax advantage for the agents. Actually, the low-income valley is populated by the unskilled agents who specialize in resource gathering. For them, building houses isn't worth the effort. The skilled agents, on the other hand, win more money when building houses. They leave resource gathering to the unskilled agents and trade construction materials with them. The agents and the AI government have therefore co-created a system where task specialization emerged. We even observe subspecialization behaviors. In this 4-agent simulation, the first agent obtains all its money from selling wood, while the second agent focuses exclusively on stone trading. Because of its high skill level, the 4th agent only buys resources and converts them into higher value houses. Of course, equality is far from being perfect because the skilled agents still get a higher income. But the algorithm was nonetheless able to find a configuration which ensured that skilled agents remain highly productive without making the economy completely unbalanced. Alright, now here are my personal comments about these results. When talking about labor division, the paper says, we do not impose these roles or behaviors directly. And, in principle, this is true. But the fact is, a predefined skill level is attributed to each agent. What's more, the skills are always distributed in the same way. 2 agents have a very low skill level, 1 agent is average, and 1 agent is highly skilled. The authors do not seem to introduce even the slightest randomness or variation here. So it's not really surprising that we always end up in the same configuration. But is it really how specialization arises in the real world? Sure, being skilled in specific domains pushes humans to become specialized. But how do we get skilled to begin with? Is it a natural consequence of society? Or could a non-specialized economic system sustain itself? By forcing skill levels, the authors prevented themselves from exploring these questions. A possible improvement would be to make skill a dynamic property that is derived from previous iterations. Also, by using a map, the authors have decided to introduce a spatial aspect in the simulation. However, this point is barely discussed in the paper. But the effect can be significant. For example, here, we see that an agent corners other agents by building houses around them, which prevents them from exploring the map. The topology of the map may also be a significant factor. Every screenshot seems to depict the 4 agents starting from each corner of the map. Thus, the fact that the map looks divided into 4 parts, separated by rivers, seems to further confine each agent in its starting territory. What's more, it looks like the map isn't homogeneous, since some agents start in regions containing only wood or only stone. This would introduce a huge bias by forcing the specialization behavior discussed before. Again, introducing more randomness and variability in the topology of the map should be a useful addition here. Due to all these highly specific aspects, it is hard to determine the extent to which these results can be extrapolated to real-life economics. The paper, nonetheless, introduces interesting avenues that could be further explored in subsequent studies.